This lesson we're looking at the fundamental theorem of algebra and complex conjugates. So in this lesson we're going to be able to use the fundamental theorem to find the number and type of roots of a polynomial function, given information about its zeros, and then using the complex conjugate to find the remaining roots of a polynomial. So what is the fundamental theorem of algebra? Basically, summarize, the fundamental theorem of algebra is a polynomial of the nth degree will have exactly n roots. So if we have a cubic, third degree polynomial, it needs to have 3 roots. If a polynomial is of a 5th degree, then it will have 5 roots. So the degree of the polynomial equals the number of factors and zeros it's going to have. Now, in the last unit, the degree was how many x-intercepts, how many times it was going to cross the x-axis. Now, the number of x-intercepts that a polynomial has is the number of real roots or zeros. Now we know about imaginary numbers and complex numbers, so we may not always have the same number of x-intercepts that the degree is. So if we have a quartic like we do over here, this one has 4 zeros because it is of degree 4, but they're all x-intercepts. They're all real solutions. So this graph here has 4 real zeros. Now this graph over here on the right side, we know that's degree 2. It's a quadratic. However, it never crosses the x-axis. But we know, based on the fundamental theorem of algebra, it needs to have 2 roots because it's degree 2. So in this case, it's going to have 2 complex zeros, 2 imaginary zeros here. So we're going to have to distinguish, looking at graphs now, do we have real or imaginary solutions? Now, before getting into some examples, there's one more theorem that we're going to look at, and that's a complex conjugate theorem. And what this states is, if p is a polynomial function with real number coefficients, and a plus bi is a root, is a zero of our function, then a minus bi is also a root or a zero. So we talked about complex conjugates, and we use those to rationalize our denominator. But what we also have to understand is that our complex roots come in pairs. They'll always come in pairs. So if we have a plus bi, we also have to have a minus bi as a zero. So there's never just going to be one imaginary solution. There will always be 2 imaginary solutions when we're looking at a polynomial function. So let's think about it. So if we have a polynomial function, p of x, with rational coefficients, and it has the roots of 3i and 2, find any additional roots. So looking at it, it tells us we have 3i and 2, so 2 is a real number, so it's just 2. But if we have 3i, that means we also have to have negative 3i, based on our complex conjugate theorem. They always come in pairs. So if we have the positive, we also have to have the negative. So even though here we're given 3i and 2, this is actually degree 3, and it has 3 roots. So if we were to sketch a graph, we would know that we'd be at 2, but we'd also have 2 additional solutions. They would just be imaginary. They wouldn't cross the x-axis. So it may be somewhere up here, like this. We'd have a graph where we have 1 real zero, and we have 2 other roots somewhere up here, but they just aren't real. There are imaginary solutions. So our summary here is, we know from the fundamental theorem of algebra how many roots or solutions or zeros a function should have. The graph can help us determine if the roots or solutions are real numbers or complex imaginary numbers. So now we're going to go ahead and look at some examples using this fundamental theorem of algebra and the complex conjugate theorem. So let's think again. this is a type of abstract question without giving a graph that we can ask that hopefully we should be able to answer based on our knowledge of the fundamental theorem of algebra and our complex conjugate theorem. So ask the question, can a quartic, something that's degree 4, have only 2 x-intercepts? And now, based on our fundamental theorem of algebra and our complex conjugate theorem, the answer is yes. So if we were to look at what this could look like, well, we know that it's got to be that W shape, and it could have 2 x-intercepts. But now we know we could have 2 complex answers as well. So we have 2 x-intercepts, 2 real solutions, and then we'd have 2 imaginary solutions. So we could have something like this. Now, if we were asked, can it have 3? Could it have 3 x-intercepts? And if we were to try and draw a graph of this, we have 1, 2, 3. The answer is no, because we have, okay, 3, but somehow this graph has to come back up, which would then give us 4 x-intercepts. And the big concept here is to remember our complex conjugate theorem, is that our complex numbers, our complex roots, always come in pairs. So there have to be 2 of them. So we could have 4 imaginary solutions. We could be all above the x-axis. Whoops. We could be above the x-axis. We could be below our x-axis. So we could have 4 imaginary, we could have 2 imaginary, but we can't have 3 because they have to come in pairs. So we can't have 3 x-intercepts because we can't just have 1 imaginary solution. So we can have 2 x-intercepts, we can't have 3. So looking at some more concrete examples here, it says name the number and type of solutions. So if we look at our graph on the left, we see that it's our W shape. We have 3 turning points, so we know that this is going to be of degree 4 here. And if this is going to be of degree 4, we know we have to have 4 solutions. And here, if we look, well, how many times does this cross the x-axis? We've got 1, 2, 3, 4. So I can have 4 solutions, and in this case it crosses the x-axis 4 times, so I have 4 real solutions or roots. So I know I have to have 4, and in this instance I have 4 x-intercepts, so I have 4 real solutions. Now my graph on the right, identify the degree. This is going to be degree 3 because I have 1, 2 turning points. So this is going to be a cubic, degree 3. If I look on my x-axis, I have 1 x-intercept, so I have 1 real solution. And that makes my other 2 imaginary or complex solutions. So identify what degree it's going to be, and then identify how many x-intercepts you have. The x-intercepts are real solutions, and then based on your degree, you know how many other have to be imaginary solutions. So you've got 2 more examples here. So go ahead and answer what the types of solutions are and how many of each for both of these graphs, and then go ahead and play the video to get the answers. All right, so for this graph on the left, I've got 2 turning points. I know this is going to be a cubic, degree 3. So I need to have 3 different roots here. So if I look, I have 1, 2, but this one here is a double root. And a double root means that this is actually 2 solutions. So I have 1, 2, 3. All of these are going to be real solutions. So I have 3 real roots here. And I know if I have 2 here, that I can't have 2 real and 1 imaginary, because imaginaries come in pairs. So that'll clue me in that, yeah, this is a double root, because I can't just have 1 imaginary solution. If I'm looking at my graph on the right, I've got my W shape, I've got 3 turning points, 4 different intervals, so this is of degree 4, so I need to have 4 solutions. Of those 4, 2 are going to be real, which makes the other 2 imaginary or complex. And those are going to be located on my graph, but not crossing my x-axis. Then the last type of examples we're going to look at is using the fundamental theorem of algebra, sketch a graph. So this first one here says draw a negative quartic function that has a double root and 2 complex roots. So if I know that I'm drawing a negative quartic, I know it's going to be of this shape. So if I sketch a graph, I know 1 has to be a double root. So 1 has to bounce off the x-axis somewhere. It can be anywhere. I say I want it to bounce off right here. The other 2 have to be imaginary complex roots, so they're not going to cross my x-axis. So I could come up, bounce off, and then have 2 that don't cross my x-axis. Now I could also sketch it like this. Maybe I want it over here, and I want to do my complex roots first and then bounce off. There's different options to fulfill this criteria here. But I need to have a double root, it needs to be negative, and I have to have my 2 complex roots as well. So for the next one, I'd like you to go ahead and sketch a graph, pause the video to do so, and then play the video and check to make sure that yours is similar to the one that I'm going to draw. All right, so it says draw a positive cubic function with a real root and 2 complex. So I know positive cubic, I'm going to start down and up, so it's going to look something like this. So if I have my axes, a real root can be anywhere. It can be on the negatives, the positives. I have a real root here. And then 2 complex roots. So I could come up and then have my 2 complex. Or I could have a bunch of different options. I could have my real root here, and I have my 2 complex, and then I have my 1 real. So different options, but make sure that you just have your 1 real and 2 complex. Your complex cannot cross your x-axis.